Okay, I'm going to do a solution for rigid body kinetics number 5. And this is actually a really important concept that this one shows you. What it's going to show is, so the result of this is a really surprising result, kind of. And it says for any collection of particles, and now, most of the questions um, in this set of problems is dealing with rigid bodies, obviously. But here we're not talking about rigid bodies. We're talking about anything you want to consider to be a single body. So it could be like a bunch of marbles out in space, or it could be a lump of pudding that's flying through the air, or whatever, any collection of particles, or it could be a rigid body, but it doesn't have to have any kind of uh, understandable relationship between the particles. So this is a really strong statement. Any collection of particles, um, if you add up all the forces on all those particles, it's equal to the mass of the particles, the total mass, times the acceleration of the center of mass of those particles. Okay. Uh, so what that's saying is, imagine you have these, 100 marbles out in deep space, and they're nowhere near each other. And you apply a force vector, a known force vector to one of those marbles. It doesn't affect any of the other ones at all. If that total force that you apply to the one marble is equal to the total mass of all of them times the acceleration, the center of mass of all these marbles that are, separated out. It's a surprisingly strong statement you can make, and there's no equivalent of this for the moment equation. Okay, but Newton's second law works for any collection of particles. Okay, so let me do the problem. And I'm going to do this I'm going to do it for 3 so you can see how it works. So let's imagine that there's these 3 objects. Here's 1, 2, and 3. They have different masses. They might touch each other. They might not touch each other. It doesn't matter. Um, you can do this whole thing with some formulas and stuff to show that it works for any number of particles. But I'm just going to do it for 3 because I think it's sort of more intuitive. All right, so what do we know? Well, we know that for each of these particles, if you add up all the forces on that particle, F net acting on particle I is equal to the mass of particle I times the acceleration of the center of mass of particle I. Right, so that's true of 1, it's true of 2, it's true of 3. All right, well, let's see if we can say something about the total force on the whole system and the total acceleration of the whole system. Well, what do we know about the center of mass of the whole system? We know that the position of the center of mass, this is just the definition of center of mass, is 1 over the sum of those masses times the mass of the first one times its acceleration. Sorry, we're doing positions, not accelerations. Mass of the first one times the position of its center of mass plus the mass of the second one times the position of its center of mass plus the mass of the third one times the position of its center of mass. Okay, so that's just using the definition of center of mass. And I'm going to rename this M total. Okay, so, and that's just a number. So now take the time derivative of both sides of this. M total doesn't change in time, and all you get is that the velocity of the center of mass of this system is equal to 1 over M total times mass 1 times the velocity of its center of mass, that individual ball's, velocity, plus M2 times the velocity of ball 2's center of mass, plus M3 times the velocity of ball 3's center of mass. And now take the time derivative again, and you get the accelerations. So the acceleration of the center of mass of this system is 1 over the total mass times the quantity m1 times the acceleration of ball 1 plus m2 times the acceleration of ball 2 plus m3 times the acceleration of ball 3. Okay. Well, now we can use this result here and rename each of these things, right? Each one of these is just F net on that individual ball. And so we get the acceleration of the center of mass is equal to 1 over m total times F net acting on ball 1 plus F net acting on ball 2 plus F net acting on ball 3. Okay. Well, if you add up the F nets on the individual balls, that's just the F net on the whole system. And so we can rename this F net, and this equation tells us that F net on the whole system is equal to the total mass of the system times the acceleration of the center of mass of the system. Okay, so like I said, this is really kind of amazing. You can see how shocked this guy is. So that says that, I already gave the example of balls out in space miles apart. They don't sense each other, it still works. Same thing with if you threw a kilogram, dropped a kilogram of pudding out of a bucket over a bridge. The net force acting on that blob of pudding is equal to the mass of the pudding times the acceleration of its center of mass. So marvel at that for a while. Okay, that's it. Number 5 from rigid body kinetics.